Okay, so let's get started again. So we just covered CBC mode. And so it's a very important mode because you will still find it in many legacy systems. But hopefully it's also disappearing. But I'm afraid that it will disappear as fast as the DES will disappear. So it takes always a long time. So in 1997, some very interesting theorem was proved. So it's interesting that cryptography became more and more scientific and mathematical. And so the foundations for this were laid in the 1980s, but most of the work was focusing on public key cryptography. And then in the 90s, people started focusing on symmetric key cryptography and trying to prove things. Now the problem is, you can't prove that AES is secure, right? It's just a bunch of equations. And maybe someday somebody finds a clever way to solve these equations, right? It's not inconceivable. It's not so likely, but maybe, you don't know. But what you can do is you can assume that AES is a good block cipher and then try to prove that CBC is a good encryption mode. So then you have to define what good encryption is. And it turns out that this also took 2 decades. It's actually quite difficult to do. But maybe the easiest definition for now is this is nonce-based encryption, so you assume that there is a unique nonce, and in this case also a secret. More or less what you say is that my ciphertext should be random bits. Okay, of course, that means you don't hide the length of the ciphertext or the plaintext, but your ciphertext is just looks like random bits for anybody who doesn't have the key. Okay. And so more or less this kind of theorem was proved. So Belair and his colleagues proved in 1997 that if AES is secure n-bit block cipher, then AES in CBC mode with random and secret IV is an encryption algorithm secure against a chosen plaintext attack. So they consider an adversary that has either ciphertext only or chosen plaintext attacks, provided that you can encrypt at most R blocks with R much less than 2 to the n over 2. That's a theorem. So there is many things you can learn from this theorem. It says that you have to use a random and secret IV. And then people indeed show that if you don't, then you have problems. Second thing is, if you encrypt too many blocks, the security will collapse. And the limit for AES n is 128. The limit is 2 to the 64. But you actually have to stay below that. And more or less the security goes down quadratically. So if you want 1 in a million security, you should stay 2 to the 10 below. You can only encrypt to the 54 bits. If you want 1 in 1,000 billion security, you should stay at least a million below it. So you can only encrypt to the 44 bits. Which is what most people more or less accept, that you should go stay a million below in practice, and the chance of breaking is 2 to the minus 40, which is kind of okay. The other thing which is interesting is it only says chosen plaintext attacks. There is also chosen ciphertext attacks. And it turns out that this theorem doesn't say anything because, in fact, AES is insecure against chosen ciphertext attacks in CBC mode. Okay, we'll come back to this at the attacks on CBC mode. So in the 70s, a second mode was being published. So there were actually, well, the third, there was ECB, CBC, OFB, and then the fourth one, CFB, I will not discuss. But OFB is actually a simple way to turn AES into a stream cipher. And this is still used in 3G, at least a variant of this. So what you do is you take an initial value. In this case, it can be public. Okay, it doesn't have to be secret, but it should be unique, obviously. And then you encrypt with AES. You use this as key stream, and then you also feed this back to the register. And next time you encrypt it again. So more or less, it's a finite state machine. The initial state is the IV. There is no key in the initial state. The next state function is encrypt the state with the key. And that gives you the new state. And the output function is just actually the new state. That's also what is being used to XOR to the plaintext as a key stream. It's called output feedback because you feed back the output. The standard allows you to select only some bits of this. There is no reason to do this because it makes it a lot slower. But of course, if you have to encrypt 500 bits, then you can first take 3 complete blocks and then 1 block with 116 bits, you check on, and then you actually have a ciphertext which is also 500 bits, which is actually very nice. In CBC mode, this is what you cannot do. This is painful, as we will see. But in OFB mode, like a stream cipher, you can encrypt any number of bits. So what are the properties? Well, the key stream is computed independent of the plaintext, so you can pre-compute it. Or if the plaintext comes in bursts, you can just have a small buffer, and this is very nice. It's independent. Very important is also error propagation. So if you have one error in the ciphertext, you only have one error in the plaintext. So for wireless communication, this is much more suited than CBC mode. The hardware people don't like OFB mode because you can only start encrypting when the previous encryption is done. So you have also this is inherently serial. Of course, there is some bypasses. You can also say, I choose 8 IVs, and then I can run 8 in parallel. But I mean, that's a bit a stopgap. It solves the problem, but it's not really very elegant way of doing things. You have to make sure the IV is different, because if IV is the same, then you have the Venona problem, transmission in depth. Then you get the same key stream, and then remember, you can XOR the ciphertext, you get the XOR of the plaintext. Then it's a disaster. Okay, so if you, in CBC mode, if you reuse an IV, you leak some information on the plaintext block. There's some attacks that are a problem, but it's mostly the IV not being random affects the first plaintext block, or if you encrypt twice the same message, you get the same result. So the IV, if you mess up IV, it's not good, but it's not terrible. If you mess up the IV, it's a disaster here, right? Because then you use twice the same key stream. So you have to make sure you don't mess up the IV. And also, if you look at this, in the decryption, you only use AES in forward mode. So you never need to implement AES decryption. So it's a small advantage to CBC that you never need to build the hardware to decrypt. Because also in the decryption, you also use the encryption mode of AES. So already in the 70s, Diffie suggested a different mode, counter mode. For some reason, it was not accepted. But then, in fact, the industry liked it so much that when the AES block cipher was published, there was a big push. And so a couple of years later, so 2003, NIST finally standardized the counter mode. So there is now a standard counter mode. And if you look on the internet, now everybody uses counter mode. Counter mode is very similar to OFB, which means it turns AES into a stream cipher. Okay? So you take a short key and you substitute to a long key. The IV is a counter, so you actually initialize a state with the IV, except for, say, the last 32 bits or the last 48 bits, the ones you want to use as a counter. And so to go to the next state of your state machine, you just increment the counter. Okay, so it's very efficient like state function. What is your output function? You just encrypt the state. And you get a key stream. And the hardware people love this because you can parallelize this, right? You can just build 2 AESs and you can shift the counter by 1 and increment it by 2, and then you are twice as fast without any other hacks. Or you can pipeline, which means, if you know what pipelining is, you can start in round 1 with the first encryption, then you can increment your counter, and while you do round 2 for the first encryption, you do round 1 for the second encryption, and so on. So you can, in fact, with AES, if you have clever hardware with 10 rounds implemented, you can compute 10 AES at the same time. And this is what hardware people love, because this is how you get these amazing speeds. This is how you get 0.7 cycles per byte also with the Intel instruction, because of the pipelining. So for the rest, the properties are the same as OFB mode, no error propagation. If you mess up the IV, if you reuse the IV, you're in big trouble, because then you get repeat. The nice thing of counter over OFB mode is you can start decrypting in the middle, because you can just advance your counter by whatever, billion positions, and then you start decrypting. In OFB mode, you can't. In OFB, you have to keep running to the OFB mode because you don't know what the state will be. So this is why people prefer counter mode over OFB mode, and I don't think you'll find actually OFB mode very much in the wild. But for some reason, the standard chose OFB in 1981, and it took 20 years to correct that. But today, you find counter mode everywhere. So again, don't reuse the IV because then you're in a serious problem. But that's today the default mode. Again, you don't need the decryption of AES for this. So it has actually quite some advantages. But don't mess up the counter. That's important thing. Or if you start your counter at 0, you have to make sure that every time you reset your counter, there is a new key. And I don't have to tell you, of course, that we've been telling people this, but of course, implementers have messed it up. Because you just tell them in the CBC mode, use random secret IV, they don't do it. In counter mode, make sure your IV never repeats. They do it anyway. Right? That's the problem. So the question is there a protection against stupidity of implementers? And I guess there is not. So when should you use ECB? Never. When should you use CBC? Well, it's legacy. There is quite some problems. OFB and counter mode have no error propagation. And counter has many advantages of OFB, so I think OFB is now also being deprecated. And there is also CFB mode, which is also something from the 80s. This was when networks still lost bits. And so somehow you didn't know how many bits you got, and then how can you keep the encryption in sync? But this is no longer a problem of 2023. So now we come back to this intriguing theorem on CBC mode. So there is this beautiful theorem. It exists now about all the modes, but only for CBC mode. I show you the theorem, which says more or less CBC mode is secure in a chosen plaintext model if you encrypt at most 2 to the n over 2 blocks. So now we're going to look at what is the problem if you would encrypt more than 2 to the n over 2 blocks. Imagine we did this. So I do an experiment. I make a very long plaintext with 2 to the n over 2 blocks. For AES, this is quite long, 2 to the 64. That's not so practical, but imagine you were using DES. Then this is 2 to the 32. That's like, a couple of gigabytes. So you decide to encrypt a movie, a couple of gigabytes with AES in CBC mode. What happens? Well, your ciphertext will be random blocks. And now there is some phenomenon called the Bertie paradox. Who knows what the Bertie paradox is? So not everybody. But more or less what the Bertie paradox tells you is that among those blocks, there will be 2 identical ones with high probability. Okay? If I have 2 to the n over 2 blocks, I expect to find 2 the same. Now, is that so bad? Because statistics tells us this should happen, and then it happens, is that bad? Well, it's quite bad because you know that if Ci is equal to Cj, that also the same holds for the encryption at the AES, because AES is a permutation, and if the outputs are the same, then the inputs are the same. So I don't know the inputs, but I know that this value here is equal to this value. And this value is Pi plus Ci minus 1, and I know Ci minus 1. And this value is Pj plus Cj minus 1. So I have this equation here, Ci minus 1 plus Pi is Cj minus 1 plus Pj. So again, if these 2 ciphertext blocks are equal, then the inputs are equal, and I write down this equation. I don't know the value, but I know that this sum is equal. And I know Ci minus 1 and I know Cj minus 1, so what I now know is the sum of 2 plaintext blocks, Pi plus Pj. So I have this perfect encryption with a perfectly good block cipher, but if I encrypt very long messages or too many blocks, I now suddenly find the sum of 2 plaintext blocks. And imagine that, one of them is a picture. I know this part is a picture of the ciphertext, and this is the sky, so it's probably all zeros or whatever. Then I actually know the other plaintext block. So it's not such innocent. You actually leak information on your plaintext. So it's clear if you want good encryption, you don't want to have such collisions because they leak information. So why does this happen after 2 to the n over 2? Let's go to the Bertie paradox. So the Bertie paradox says that, let me first tell you the story. If you have 23 people in a room, you have, with high probability, 50%, 2 with the same birthday. So if we had time, we could do this, but maybe do it in the next break. So 2 people here must have the same birthday. Amazing. So why is this? If you have 23 people, the number of pairs of people is not 23 squared, it's 23 times 22 over 2. Okay, that is 23 times 11. That's 230 plus 23, so that's 253. So in this room, there is 250, well, if you have 23 people, we have a bit more. You have 253 pairs of people. And each pair has a probability 1 in 365, assuming birthdays are randomly distributed, to have the same birthday. So you see, actually, not so surprising that actually this is 50% chance. In fact, it is 50% chance exactly for 23. So if you now would ask the question, who has their birthday today? Okay, for 23 people, well, there is 23 birthdays today, and each of them has probability 1 in 365. So in fact, it's a very small probability that somebody has their birthday today. It's 6 or 7%, while in fact, for the same birthday, it would be much better. Okay. I once did this experiment, and we went to the whole room, and all the birthdays were different except for the last 2. They were twins, and they were sitting next to each other. So there is also Murphy's law, you shouldn't try these experiments. But, so here is the mathematical formulation. I have a set of S elements, so this is the days in the year. Choose R elements, this is the students in the classroom, at random. Okay, so they can have, so there's no constraints. The probability P that there are at least 2 equal, so that 2 have the same birthday, is given by this expression. You can prove this, and it's proven on the slides. I will not go to the math. It's very elementary mathematics. With some Taylor expansion and some simple approximation, you can prove this. So more or less, this is for S large. So this expression is not very accurate for birthdays in 365, but if S becomes large, like in cryptography, then it's a very good approximation. So more or less, you can also drop the -1. And if R is about the square root of S, my probability is 39%. And then the thing is, once it goes up above this limit, it grows very quickly to 1. So what is to do with the ciphertext here? If I have a large number of ciphertext, and this is a space of 2 to the n, my S is 2 to the n. If I select R ciphertext, which is 2 to the n over 2, I expect with high probability to find a collision. So this is how the birthday paradox applies here. Here is the mathematics. You can look at this. It's not very difficult. We actually know even more. We know that that the number of collisions is Poisson distributed. So with expected value lambda, which is the number of pairs, R times R minus 1 over 2 divided by S. The expected value is just the number of pairs divided by the size of S. So by S, the size of a set. So in fact, the birthdays are distributed, the expected value is this value, and the distribution is Poisson, which is given by this expression here. So e to the minus lambda times lambda to the c over c factorial. So you can easily compute what is the probability to have 0, 1, 2, 3, 4, 5 people with the same birthday, given that the number of people grows. So here it's applied to CBC mode. So the ciphertext block Ci are random n-bit strings from a space of size 2 to the n, with n the number of bits. If I collect R is square root of n to the n over 2 ciphertext blocks, with probability something like 39%, I will have 2 identical ciphertext blocks. So, which means Ci is equal to Cj, and then I can find out the sum of the corresponding plaintext blocks. So this is a big problem. So in practice, for DES n is 64, 2 to 32 64-bit blocks is 32 gigabyte. Of course, in the 70s and 80s, hard disks were 20 megabyte, and gigabyte was something which people could only dream about to have as storage. Today, your hard disk is terabytes, and so in fact, this is nothing, right? So this is a problem. For AES, the leakage will only happen after exabytes. Now, this is a bit misleading. Well, you're quite sure it's going to happen, but very often your boss will say, I don't want something to happen like this, probability less than 1 in a billion, right? If your boss says that, then you have to, well, I hope he doesn't say it, because then you have to actually go, the probability is quadratic, you have to go down with a factor to avoid this problem, Okay, so and in fact the problem is worse because of the Poisson distribution. So if I say I have a DES encryptor of 1 gigabit per second, this is old stuff. Today we have much faster encryptors. So after 4.5 minutes, I expect already a collision. So even if you just use a key for a few minutes, and this is not a high-speed link, right? This is a normal connection. Then after 4 minutes, you start leaking information of 2 plaintext blocks. Now, after 19.5 hours, say you wait for a day, you now have collected 2 to the 40 ciphertext blocks as an attacker. So now you can compute the number of collisions with this expression here. So the expected number is r times r minus 1 over 2s. Okay. So this is 2 to the 40 squared. I drop the minus 1. It drops here. Divided by 2 to the s plus 1 to the 65. So I have already 2 to the 15 collisions. So in fact, after 19 hours, you have 32,000 collisions, which means you have 32,000 relations between plaintext. Of course, you can argue this is, of course, you have a huge number of plaintext as well, 2 to the 40. But still, this means a lot of information starts leaking. Okay? So at the exam, I sometimes ask you to calculate this, and then some people say, oh, 19.5 hours, then I have 2 to the 40 up to the 32, because I get 1 after the 32, so I get 2 to the 8. No, the collisions grow quadratically, not linearly. Right? So it's r squared over 2 to the n plus 1. So if you increase the time you wait by a factor, in fact, in the equations, r goes squared. So it's not a linear increase of collisions. Collisions grow quadratically with the number of text collected. So the answer is to make sure that you change your key quickly. So you see, for DES, you should change your key probably every second or so. And then then you can compute the expected value and the probability of having a collision with the Poisson distribution. And then, depending on what your boss says, can it be 1 in 1,000, 1 in a million, 1 in a billion? You have to adjust your parameters. But if you want a very low probability of something bad happening, you actually have to go very much below and change your key very, very frequently. So now you understand why for AES we chose 128-bit blocks. Because with 128-bit blocks, at least you can encrypt gigabytes without being in trouble. Right? Then suddenly n becomes 128 and the problem goes away. It's only for very large things. So this shows that in the security bound, if I exceed 2 to the n over 2, I have a problem. So even if I come close to it, I have already a probability of problems. Second thing is, this result says that CBC is good against chosen plaintext attacks, but what about chosen ciphertext attacks? So assume that I just take a ciphertext consisting of 3 blocks, okay? And I take them the same, and I decrypt. I don't know the key, but I ask for decryption. Then I know that I get something out here. The IV will be Abbott, which I don't know, and I get a block. But then C will be decrypted. Then the C will be Abbott, and I get P. And here I will get exactly the same as here. Right? And if I would have 4 blocks of C, I would get always the same plaintext out. Right? You see this? That if you look at the decryption, if I take identical ciphertext, what happens is after 1 block, everything becomes the same, and I get here the same thing. So as cryptographers, we say this is bad, because for a really random cipher, if you put in identical ciphertext blocks, you just get random plaintext blocks. So it's a bit the opposite from the picture I showed you, but this is also bad, and there is attacks that exploit this. Okay? So for example, in TLS or in SSH, as we will see, they were used to encrypt passwords in CBC mode, and then you can use it to actually guess password byte by byte, character by character. So more or less, CBC is completely insecure against chosen ciphertext attacks. So this theorem doesn't say anything about it. And in fact, we understand why, because it's not secure against chosen ciphertext attacks. Now, in real life, chosen ciphertext attacks are feasible, because if I have a TLS connection or an SSH connection, I can sit in the middle and change some bits of the ciphertext and see what happens. Right? Maybe you will get error messages, and it turns out that those messages give you information on what the plaintext was. So you need a mode that's secure against chosen ciphertext attacks. So now you understand better why I explained to you that you should use encrypt then MAC. Because if you encrypt then MAC, then the ciphertext is MAC'd, and the first thing the recipient does is check the MAC. And if the opponent played with the ciphertext, the MAC will no longer work, and then I stop. I never decrypt because I could leak information. And so if you have encrypt and MAC, you don't need encryption secure against chosen ciphertext attacks, because the MAC protects you against chosen ciphertext attacks. And so this is why, another reason why we want to dedicate to encryption, to avoid chosen ciphertext attacks, to stop them, to protect the encryption against it. But still, it's possible to make encryption secure against chosen ciphertext attacks without the MAC. There is other solutions, but this is what today is the default solution. So now why is this a problem? So it was a very good point made. So what to do with incomplete blocks? And it's very interesting because every standard does something else. So some standards say, well, you put just a 1 and then zeros. Why do you put a 1? Because if you just put zeros, you don't know where it, maybe your plaintext had zeros as well. So you put always a 1 and then zeros. This is a bit annoying because if now your plaintext was exactly the right length, you still have to put a 1 and 0, so you lose a whole block. But that's what it is. And SSH, what you do is, at the end, you put x bytes of x. So if you have to put 7 bytes, you put 7 bytes with the value 7. If you have to pad 3 bytes, you have to put 3 bytes with the value 3. And this is how you can configure where, look at the last value, then you can see where it ends. So it's a byte-oriented, but not bit-oriented. There is also a very clever trick called ciphertext stealing, whereby you can actually you cheat a bit and you encrypt the last part in OFB. It's actually very neat, but then you have to decrypt and encrypt in reverse order the last blocks, and some implementations find this annoying. So there is clever, people have worked on this problem and there is solutions, but in general, then you open yourself up to new attacks again. So here I will show you an attack. So we will follow the suggestion of Joris, so you put the plaintext length in byte in the beginning. So in fact, then the standard still decided to actually put 100 at the end, and we assume here that my plaintext has one more byte, so the last byte of the password in the last block, okay? But the length actually is in the beginning because we decided in this application it was possible to know the length. So we have kind of a double protection. We have the plaintext length in bytes, and we have here a 1 and 0s. So what I now will do, okay, I will actually try to guess the byte of this password. I will try to guess the last character of the password. And I will XOR this to the C2. And I can also XOR here 10000. Okay. So what will happen is if you XOR something to C2, well, what comes out in this P2, this is garbage. Okay, this is messed up. But the nice thing is, if I XOR something here, we know that it will also be XORed here, and I now XORed this P3, XOR my chosen string, plus this 1001. Okay? So I can more or less choose what appears here. Okay? Assume now that I guessed, so I took his 1100110, I guessed that this was the character of the password. Suppose my guess is right, okay? Then I get a 0 here instead of P3, right? Because I XORed the right value here, I XOR this to P3, I get 0. I also XOR here 1001, I XOR this, so I get 0. In fact, my last block consists completely of zeros, okay? So if I guess the right value of this character of the password, namely 11001100, and I XOR this string, then the last block will be completely zeros. Well, what will happen if you decrypt? You will write software for this, and you will say, this can never happen. Because the first block told you the length, and so you expect to have, in this position, A1. Okay? And it's not there. So in fact, as a good programmer, you've been told to do the paired parsing, and you expect to have a 1, and if there is not a 1, you say 1 missing in the right place. And you even tell the sender what went wrong. Now it turns out that if you made a wrong guess, this doesn't happen. So in fact, you can check the guess for the last character of the password. And once you have that one, you can continue and byte by byte guess the password. And this is how SSH and TLS actually got their, was shown to be vulnerable against these attacks. Okay, so what is the solution? Well, the solution that people conceived was, let's think very carefully about the padding and let's not give error messages, which goes against programming principles. But people said no error messages, because then if we tell what's going wrong, it will be used to find information. And then, okay, people said, now it's solved, we go to the error message. Then people found out that, in fact, if you look at the code, the time it takes to answer depends on which path you followed. And by measuring the cycles that we took, even at distance, you could actually guess whether your password guess was right or not. And then somebody wrote constant time implementation. I think somebody at Google, Adam Shostak did this, I think. He finally managed to do it. Okay. And then people still found the problem. It was a lucky 13 attack. And then Google said, we give up, we go to RC4. We're like, what? And then they went to Cha-Cha-20. But Google never wants to use CBC mode anymore in anything because they got traumatized by this. That Adam Shostak spent months and months coding this thing in constant time, and then people still found that there was still some special case where a special length, there was a bug. And same thing, Amazon, they also tried to implement it. They also said, here's our implementation, constant time, failed. So this is why the internet has abandoned CBC mode, because we can't do the checking of the padding in constant time. And so people just say, let's go to counter mode. Now, counter mode has other risks, because in CBC mode, you have the padding problem and you have the IV problem. But if you mess up the IV problem, you have some problems. They're bad. But if in counter mode you mess up the IV, it's terrible. So I'm not sure it's so much better. It's always difficult. That's maybe the main message. Okay. Then what about OFB mode? So for those people who took my algebra class, or those who took a basic algebra course, they know that if you have permutation and you keep repeating it, you get cycles. Right? So every permutation can be written as, so what happens is, if you start from a point and you apply the permutation, eventually you will end up in the same point. That's what happens. And so you can study the cycle structure of permutation. This is very well known. Mathematicians have studied this. And more or less, 61% of all the points lie on one big cycle. So in fact, with a very high probability, if you're more than 50%, you're lucky, and you're on a big cycle. And so it means that this sequence will not repeat for 2 to the n times 61%, or I'd say 2 to the n minus 1. Half the points are on a cycle, more or less, more than half. By the way, there is also with probability 1 over e, 1 over 2.7, there is a cycle of length 1. Which would be really terrible because it means you always produce the same key stream. But the chance of hitting that is very small. The probability of ending up on a cycle with length c is c over 2 to the n. So the probability of ending up in a cycle of length 1 is 1 over 2 to the n. It's very small. So you don't care too much about it. So OFB mode has a different problem. So in fact, the cycle structure is okay. You will likely end up on quite a big cycle, and you don't have repetitions in your key stream. The problem is you don't have repetitions in your key stream. Because in a random key stream, you do have repetitions by the Bertie paradox. So if you have a key stream with no repetitions, it means it's not random. Which means you leak information on your plaintext. And people were laughing at this, but a couple of years ago, somebody wrote a paper showing really you could deduce information on a plaintext from this. It was applied in an attack on TLS with a 64-bit block size still being used. So because it doesn't repeat, it's not random. Because in a random sequence, it repeats after the n over 2 by the Bertie paradox. And this leaks information. It's a deviation from randomness. So more or less, the message is in OFB mode, you should not use the same key for longer than 2 to the n minus 20 blocks. Okay, so you can take 2 to the n, well, in fact, 2 to the n over 2, minus your security factor to the n minus 10 or minus 20, depending on how paranoid you are. That's how many you can use. So that you, in fact, at that moment, the probability of a collision is small anyway, so the fact that there is no collision will not harm. So it's a bit counterintuitive. The cycle is very big, but still you can only use a very small part of it. And here is the mathematics of this. I will not ask it at the exam, but if you like to figure it out, it's not so difficult, right? This is all just some basic probability theory, but I'm not going to spend here 10 minutes to explain that to you. I will not ask calculations of this kind of level. If you like it, you can look at it. You can also look this up. Today you can ask ChatGPT. They will give you high probability the right answer to these kind of questions, and even explain to you how they come at the formula. Let's go back to a very funny detail. So in the beginning, when the draft standard was out, some people said, can't we feed back only half the bits? Right? Should we really feed back all the n bits? Because I guess they had some reason to simplify the hardware. Is it not enough that we feed back a few bits? And then people actually said, well, it turns out that even if you feed back only n minus 1 bits, instead of n bits, then the update of the state is no longer a permutation, which means you can now have two distinct states with the same result afterwards. And mathematically, this makes a hell of a difference, because now you end up, if you start iterating, you can hit an earlier point, and we call this the row shape. So you can end up on a cycle. And mathematicians have studied this, and they prove that after 2 to the n over 2 steps, more or less, you end up on a cycle of 2 to the n over 2. So in fact, you now get repetitions which are really, really bad. Because once you're on a cycle, you know what's coming next. It's not just one random repetition, everything comes. It's actually terrible. So if you would feed back n minus 1 bits, so you have a bug in your code or so, or you decide that feeding back fewer bits is okay, no, it's not. If you don't feed back the full n bits, the security completely collapses. And in fact, you only have security for a very short cycle. So in fact, the whole, if you call the functional graph, looks something like this. I just showed you what happens if you start in one point, like it's kind of some hairy thing with all these things that come together. And so you expect it to end up very quickly on this short cycle. And finally, counter mode. Counter mode is very simple, because in counter mode, this is the case where the counter is the full length, which you don't see very often. So you start at 0 and you run to all the values. But you can make a similar reasoning for other values of the counter. So, well, that's very simple. Everything is on one big cycle of 2 to the n. And you're sure that your output sequence will never repeat. Okay? But again, that's a deviation from randomness. Because in a random sequence, you get repetitions. And here you don't get repetitions. So this leaks, again, information on plain text. Now, the way counter mode is used in practice is slightly different. So what people do is they pick a random IV of, say, 96 bits, and then they limit their plain text or the counter sequence to 32 bits, so because most packets of plain text are to the 32, 128-bit block, so it's a bit more, it's like gigabytes. So they pick random IV, and then they start incrementing from the IV. Okay, so it means you have these blue arrows. You always use part of your cycle. But of course, if you choose too many IVs, by the Berti paradox, 2 of those can overlap and you have problems again. And the problem is bigger than if you use one big cycle, because now, again, once it starts overlapping, everything will be the same. So the main message is it's very important how you use a block cipher. That's one. Right? So the mode matters, and you can mess up the mode in many ways. And this is now standardized, but it's still a topic of research. There is people who still want to get better features and better properties, especially in combination with data authentication. That's one thing. Second thing is modes fail in very subtle ways. Right? And more or less, the main message is if you have a block length of n bits, you can encrypt at most 2 to the n over 2. I don't show you a mode in the simple modes that can do more than 2 to the n over 2. Okay? Now there is, we call this beyond birthday modes. People have done research on finding modes where you can use more. But this is like too advanced. We're not going to study that. But the standard modes that are in the standards and are standardly used, you can only use 2 to the n over 2. But then you also have to think that means that you're sure it will go wrong at 2 to the n over 2. So you actually have to subtract 10 or 20, and sometimes the security goes down linearly, sometimes quadratically. So you actually have to think of what is the probability that something can go wrong in my system. So in fact, with AES, you can't say, oh, I can go to 64, it's okay. No, in fact, if you're low risk, you can only go to 2 to the 44 or so. And that's a limit that today is still far away, but in 10 years, when you will be in charge of something, in fact, you have to start worrying about this. That even AES, you cannot just encrypt anything because you have to change your key because of the problems in the mode. So the security level is much less than you think. You have a huge key, you have a large block length, but in fact your security is only some 2 to the n over 2 minus 20 or so for AES, so which is 2 to the 44. Well, finding the key is hard, but you cannot use the same key with more than that many blocks. The real problem in practice, of course, is how to make sure the IV is used correctly and how do you make sure the key is generated correctly. Those are much bigger problems. That's where the things really go wrong, right? This is nice attacks cryptographers worry about. In practice, there is hard-coded keys still. Huh? People wrote scripts to go to GitHub and find all the hard-coded keys in the code, and they keep finding new ones. Because that's what developers do. They develop and then they need a key, they just write it in the code. That, of course, then cryptographers can't help you. We're completely powerless if you do these kind of things. Okay, then the final thing. So we'll stop a bit earlier today then. I will not start a new thing, so next week we'll look at hash functions and MAC algorithms. So what about hard disk encryption? So to show you that there is many other problems. So hard disk, they work by sector. A sector is 512 bytes. And you can't store an IV, or you can't choose an IV, because where would you store it? Well, you can do this. But if you do this, you need 128 bits. So the 16 bytes, I think your customer will be very unhappy. If you say, here is a hard disk, but in fact, every 512 bytes, we take 16 bytes away for storing an IV for encryption. Okay? So, no IV, this means if you would store twice the same information on the hard disk, you get the same result. But what people want, they want a cipher that encrypts the 512 bytes at once, so that at least if these 512 bytes differ somewhere, then the whole block looks different. And so this can be done. This is called the XEX, or XOR encrypt XOR mode. So what you do is, you take the sector number. This is known for a hard disk, which sector you're encrypting. So this means also that if you send the same block to 2 different sectors, you will get a different result. So you can, by comparing sectors, find out whether they have the same content. So you actually, with a special key, you generate an internal secret. And this you XOR to the plaintext and the ciphertext before encrypting with AES. Okay? And then you will update this key. You do this by a multiplication in a finite field. So this is, you can imagine, this is a bit like integer multiplication, but it has slightly different properties. So you multiply this. Of course, alpha should not be 0. I should add it's not be 0, because that would be really terrible. Then the result here is 0. But so alpha is non-zero. So you get a different value which you XOR to plaintext and ciphertext and so on. And so this way, if you change 1 byte in the sector, it will be looking different here. So at least this block will be completely different. It doesn't affect everything. That's not possible with this mode. There is also modes that are even more complex, where everything depends on everything. You reverse it and do it again or something like this. But this is a simple mode where any local, if you encrypt the same block to a different sector, or you change somewhere 1 byte, you'll get a different ciphertext. So this is what's being used for hard disk encryption. And there is no IV. The sector ID is kind of used to randomize the encryption, but it's a compromise. Okay, so to wrap up, so there is lots of standard block ciphers. Sorry. The block length keeps increasing. You need a mode. Yes? I think that they don't want this because it makes it too easy to flip bits. So they want some level of authentication. It's not really authentication because you can't detect changes, but they don't want to make it harder to change individual bits. So it's a bit of fuzzy property, but this is what counter mode people don't like, because then you can flip individual bits. And here you can not do it, because if you flip a bit of the ciphertext, then you will at least mess up 120 bits of the plaintext. But you can't, for example, reorder blocks. That will not work, right? And you can't flip blocks. So you don't get full data authentication. You can't get it without redundancy, but you get something that's close. So it's a bit of a compromise. I'm not saying this is the best thing to do. The best thing to do would be use modern authenticated encryption. I mean, there is better modes for this, like counter mode with CBC MAC or counter mode with GCM, the GCM mode. But you don't have space. You don't want to use the IV for this, or they can't use the sector number for IV. So it's yes. This is not XOR, this is multiplication.
Okay, sorry.
This is not the same as this. This is XOR, this is multiplication. Okay, so block ciphers are like Swiss Army knives. They're easy to make secure. For stream ciphers, there is still not many standards. By the way, I forgot to mention this, but what, for example, 3G uses to encrypt with Kazumi, they combine the output feedback mode with the counter mode. Why do they do this? It has disadvantages of both. But they do it because they took a patent on this. And so if you connect to a 3G network and you can decrypt things, then you must violate the patent and violate the trade secret. So they kind of, this is a way to control, cryptography is used to a way to control access to communication systems. So it's a stupid mode. Well, it's not wrong, the mode, but it's kind of, you would never do it, but they made a special mode to prevent some other country from using the same standard and hooking up without paying the license fees or without being nice. So there is less standards, operates at bit byte word level, and they tend to be simpler. So, and they give you a better throughput per area. So if you care about very high speeds without having special hardware or very high speeds in compact hardware, then stream ciphers are still used. And so like in 3G, 4G, 5G, we still use stream ciphers. In Wi-Fi and Bluetooth, in fact, we use AES in counter mode. Or we don't use stream ciphers, which are designed for it, we actually decide to use AES. So again, we're in favor of public algorithms. I don't think there is anything widely used that's now secret. As I mentioned, the implementation method may be secret to stop side channel attacks, but the algorithm itself are no longer kept secret. Okay, so we'll stop here. And next week there will be no lecture. And the week after there will be 2 lectures, right? One on 16th of October at 2 o'clock, because the administration decided that 2 o'clock is better than 4 o'clock. And I cannot contradict the administration. Never do that in your life. And then, so we have 2 lectures that week, and then the week after you have no lecture. Okay, that's more or less the schedule. And by the way, this capture the flag competition. So there is also in March a big competition.